In the last session, we saw a data structure called graph. We looked at the basic definitions of graph and the terminology and the properties of some simple properties of the graph. We also saw that many real life problems or applications or scenarios can be modeled as graphs. We look at now some procedures on graphs which are going to help us to solve problems. One obvious problem that comes to mind is, if you are given a graph, how do you traverse in a graph? Or simple, if your graph is representing a route network in a city, then given two cities, you would like to know if there is a route between the two cities, or one can think of many such applications. So, crucially this means, given a graph, how do you traverse a graph? If you recollect, we already have seen traversal in a tree, and we know that trees are also particular type of graphs. So, by traversal we mean a systematic way of going through all the nodes or all the edges in a graph. So, in this session we look at the problem of traversing a graph. So, traversing of a graph typically includes searching for a certain node or traversing all nodes in a graph. Again, if the graph is representing a map of a city and you want to find a particular city and way to that particular city or a point, you need to understand how you are going to traverse the graph. There are two main ways of doing it. One is called the depth first search and a breadth first search. In a depth first search, once a possible path is found, we continue the search until we reach the end of this path. In breadth first search, start several paths at a time and advance in each one step at a time. Let us look at a real life scenario that we come across quite a few times. Suppose we want to find a way to a place in a city and we are not sure about the exact route. In practice, typically what we follow is a depth first search to solve this problem. So, we start with the path, keep on going ahead on it, asking for directions. If at any stage it is said that you got a wrong direction, you go back to a place from where you had reached this place and take a different direction from that point. So, depth first search is something that we do quite often in real life. In fact, many of our search procedures that we do can fit into depth first search. So, depth first search is a more natural way of traversing or searching a graph. So, let us look at depth first search. So, a depth first search in an undirected graph is like wandering in a maze with a string and a can of red paint without getting lost. Right? You are in a maze and you are at a particular point and you have to find a way out, and crucially without getting lost. So, suppose we start at a vertex S. So, we tie the end of our string to that point and paint S visited. So, at a starting point, to mark that we have already visited this point, we mark it visited. Next, we label S as our current vertex called U. Next, we travel along an arbitrary edge u v. So, U is just a labeling of S to make the procedure easy to write. So, we are starting at S, marking it visited, and calling it u just to indicate that this is the current vertex that where we are. So, current vertex is going to be denoted by u. At the initial point, u is going to be equal to s. Now, we take an arbitrary edge which is incident on u. If this edge leads us to an already visited vertex, we return to u. So, initially when we start, the first edge that we are going to traverse will always lead to a vertex which was not visited earlier. But as we go deeper in our path, it might happen that the edge that you traverse leads to a vertex which has already been visited. So, if the edge u v leads us to an already visited vertex v, we return to u. That is, if something is already visited, we return back to the position from where we reach that particular vertex. If the vertex v is unvisited, we move to v and unroll our string and paint v visited and set v as our current vertex. So, the edge that we have currently explored leads to a vertex which has not been visited. We unroll the string and move to v and paint v visited. The string is being maintained so that the way is not lost as we go ahead in the path. Now, this process terminates when our backtracking. So, when we move back, so when we return, if we encounter a vertex which is already visited, this returning procedure or returning is called a backtracking procedure. So, the process terminates when our backtracking leads us back to the index that we started and there are no more unexplored edges incident on S. That means, we have reached a dead end, and from dead end means at a vertex where there are no unexplored edges. As we reach that, we keep backtracking and this backtracking leads it back to S, and we see that there are no more unexplored edges incident on S. So, depth first search is going to terminate at that particular state or that particular stage. So, the simple recursive depth first procedure is, so given a graph and input vertex v in a graph, a labeling of the edges as discovery edges and back edges. So, the output is going to be, we are going to label the edges as discovery, that means an edge which leads to a vertex which has not been visited, and back edge will mean you reached a vertex which is visited. So, you come back to or you backtrack to a position from where you have taken this particular path. So, the depth first search algorithm will start with a vertex v. So, you start with the initial point in your graph from where you are going to start your traversal, that is the start point v which is given, and the output is going to be labeling of all the edges as discovery edges or back edges. So, for each edge e incident on v, if the edge is unexplored, then let w be the endpoint of e. If vertex v is unexplored, if edge e is unexplored, then let w be the other point of e. If vertex w is unexplored, then we are going to label e as a back edge, as a discovery edge, and we continue our procedure from w. So, w now becomes our current vertex. So, current vertex is v initially as we start, we take an unexplored edge which is e and let w be the endpoint. If w is unexplored, we are going to call e as a discovery edge. That means, we have discovered an edge or we have discovered an vertex which is not visited At that point, we make our W as the current vertex and call DFS on W. If the edge leads to a vertex W which has already been visited, then we call E as a back edge. So, the depth first procedure, the parameter input parameter is going to be a vertex, that is the beginning vertex from where the traversal will start, and output will label the edges as discovery or back edges. Simple property, it is going to visit all the vertices and edges in a connected component of V. We know that if a graph is connected, then given any two vertices, there exists a path between two vertices. So, if V belongs to a connected component of a graph, then all the edges and vertices in this graph are going to be visited during the DFS procedure. So, it is a simple property which follows directly from the recursive algorithm for DFS. Let us illustrate our procedure using a simple example. In this example, we are using the following convention. We have unexplored vertices which has a blue background, visited vertex X as a violet background. So, these are the vertices which we visit and going to mark as visited. The black lines are going to be the unexplored edges. So, at every vertex the unexplored edges are going to be marked with a black line. Once we traverse an edge and discover a vertex which has not been visited, is going to be marked with blue and arrow and would be called a discovery edge, and the other edges will be called a back edge. So, we are starting here with A. So, this is the first starting point which is given as a parameter, input parameter to the DFS or to the DFS procedure. Now, we are going to look at all the edges incident on A, and randomly one can choose which edge to traverse, or one can also have a order on the edges and decide to use that order to traverse the edge. So, one can have at looking at this an order on the edges, or one can randomly choose an edge which has not been explored. In this case, we are choosing this edge to be traversed first or to be explored first. Now, as we traverse that, we reach B, which we know is unexplored, right. So, we mark it as now visited. So, once we reach B, we mark it as, so initially B was not explored. Once we traverse the edge AB, we reach B and we mark or we color B as visited, and we make this edge as a discovery edge, because following this edge we have reached a undiscovered vertex. Now, we will make our current vertex as B. So, we call now DFS at B. So, initially we started with DFS with input parameter A. Now, we will call here DFS at B and continue. Now, as we do, we see that if we will only travel a edge which is unexplored. So, if we go back by this, this is already an explored edge. So, we are not going to traverse back to A. Now, we look at there is only one edge which is possible to be, which is unexplored. So, we will take that and go to C and mark C as explored or visited. So, every time we traverse an unexplored edge and reach a unvisited vertex, we mark it as visited. So, as continuing. So, then we will call DFS procedure at this particular node. Now, again there are, so this edge is already explored. So, there are three possibilities, or there are three unexplored edges incident on C. We choose this and observe that this edge actually leads to a vertex which has already been visited. So, that means this vertex or this edge leads you back to the point where you started. So, we skip that or we mark this as a back edge. So, that edge is not going to be followed, because this does not take you to a new point in your search. So, you come, so at this particular thing you come back to D. So, you backtrack to D from where you had reached A and take the next unexplored edge incident on D, which is this. So, this becomes a, so this is a back edge because it takes you back into the search. This is a discovery edge because now this leads to a edge which was not visited earlier. Once we are here, we again continue DFS at this point and we see that there is only one unexplored edge incident on D, which is this, but it leads back to A, which is already visited. So, we backtrack to D. Now, at D we see that there are no further unexplored edges incident on D. That does not mean we have exhausted all or exhausted visiting all the nodes. So, as you reach backtrack to D and see that there are no unexplored edges incident on D, you decide to further backtrack to a point or to a vertex from where D was reached. In this case, it happens to be C. So, you backtrack to C. So, you are going to backtrack once here and then you are going to backtrack here. At C, you realize that or you find that there is still an unexplored edge which is incident on C, which is CE. So, that is followed. So, that becomes a discovery edge and we paint E or we mark E as visited and we again continue the procedure at E. There is only one unexplored edge at E, incident on E, which leads it back to A. So, we mark this as which is already visited. So, this becomes a back edge. So, we backtrack to E, we see that E has no unexplored edges. So, we backtrack to the place from where we had come at E, which is here. We see that at E there are, at C again there are no unexplored edges. So, we backtrack to B to check whether there were some unexplored edges left incident on B, which were not followed or which were not explored. We are from C we are going to B, but not to D because at C we have reached from B. So, we will go to a point from where we have originally reached to point C. So, we will go to B. At B we see that there is nothing explored. So, we go back to A and at A we see now there are no unexplored edges. So, all the edges at A has been already explored. So, at this particular juncture your DFS procedure will terminate. The analysis of DFS is simple. Setting or getting vertex edge labels takes a constant time. That is, if you want to mark a particular vertex to be visited or mark it to edge to be discovery or back, it just takes a constant time. Now, each vertex is going to be labeled twice, once as unexplored and once as visited. Similarly, each edge is going to be explored twice. If n is the number of vertices and m is the number of edges, we see that DFS runs in time order of n plus m, provided the graph is represented by the adjacency list structure. We will see that unlike sorting and searching now, the analysis of algorithms or procedures which are going to be based on graphs will depend upon how the graph is represented in the machine. For example, in this case we see that an adjacency list, if the graph is represented or stored as an adjacency list structure, then the time taken is going to be order n plus m. A good exercise is to check what would be the running time or the worst case performance of DFS in case the graph is represented as adjacency matrix rather than the adjacency list structure. Now, this procedure of DFS can be used in many applications. We already had mentioned right at the beginning of the session that in practice, whenever we try to find a path, we always end up doing depth first search. We never start at the point and take all possible roads from that and keep on trying them to reach a particular destination. We begin with a destination, we begin with a path, try to follow it as long as possible, we are on the correct. At any point when you feel that it is completely wrong or there is nothing or there is a dead end, you come to turn back and then take a different direction. So, obvious application of DFS is path finding, right. So, if you are given two vertices u and z, DFS can return the path from u to z. So, we start with the DFS with u as your source vertex or u as your input parameter. A stack S is keep to track of the path between the start vertex and the current vertex. As soon as the destination vertex z is encountered, we return the path as a content of the stack. Okay, so, you simply let the source or the origin of the origin vertex to be the input parameter for the depth first search. Recursive procedures will require stacks to be used as data structures in implementing the DFS procedure. As soon as z is encountered, and definitely if the graph is connected, z will be encountered. If z is not encountered, would mean the graph is not connected. If the graph was connected, the z would definitely be encountered, and the stack contents will return the path from the source to destination. This path finding also can be extended to check whether there is a cycle in your graph. In this case, you would have to just extend the path finding algorithm to the case where your source and destination vertices or your origin and destination vertices are the same. So, this DFS gives very crucial information about the graphs that we are going to work with. First, it will tell you whether there is a path between any two given vertices that will decide whether the graph is connected or not connected. It also will tell you whether the graph has a cycle in it or not. So, if there is no cycle in a graph, then we know that it might be if it is connected a cyclic graph, then we know it is a tree. So, if the graph is connected and DFS returns that it is a cyclic, that is cycle is not present, then we can infer that the graph is actually a tree. Let us look at the other procedure, which is breadth first search. So, unlike in DFS, where you follow a path as far as possible, BFS tries to search all the paths starting from the source vertex. So, what it does is it looks at S, which is the source vertex or the origin vertex, looks at all the edges incident on S, explores them first before exploring the other edges. So, all the edges which are going to be incident on the current vertex are going to be explored first. So, this is very unlike DFS, where instead of where a particular path or particular path was explored as far as possible. So, BFS makes use of a queue rather than a stack to store the vertices which are already visited and expanding the path from the earliest visited vertices. In the first round, the string is unrolled the length of one edge and all of the nodes that are only one edge away from the anchor are visited. So, in breadth first search, we are going to visit all the vertices which are adjacent to the starting vertex or which are at a distance 1 from the starting vertex. In the second round, all the new edges that can be reached by unrolling the string, 2 edges are visited and placed in level 2. So, now you look at all the edges that were visited or were at a distance 1 from the original vertex. Now, at all these vertices you travel further a distance 1 unit away. So, in the second round all the new edges that can be reached by unrolling the string, 2 edges are visited and placed in level 2. This continues until every vertex has been assigned a level or every vertex has been visited. The label of any vertex corresponds to the length of the shortest path from S to V. So, this is a very crucial consequence of breadth first search, which did not happen in depth first search. It is easy to imagine and easy to illustrate that when you do a depth first search, you may not always get the shortest path from source to destination. It might happen that the path which is written by depth first search is longer than the shortest available path. But in breadth first search on a graph, the path returned between 2 vertices is always the shortest path between the 2 vertices. So, that is a simple pseudocode for breadth first search. So, it starts with the initial vertex S and with a Q. Initially, you want to create a so you are going to start initially with all the vertices which are going to be adjacent to S in the Q and keep on exploring edges at the first at level 1, then level 2 and so forth, and we are going to mark them as discovery edge if it is a unexplored edge. Let us look at a simple illustration of that breadth first search. Again, we are going to have unexplored vertex, visited vertex which are going to be marked, unexplored edge, discovery edge and a cross edge. So, we start again with A as our input parameter. So, we are starting our search at A. So, we will call BFS A. Now, in the first stage we will visit all the vertices which are at a distance 1. So, initially L0 has only, so L0 which is the Q initially has only A inside it as a Q. Now, we will insert B and then C and then E and so D, and all these vertices are going to be discovery edges. So, L1 will have B, C and D. So, starting with the source vertex, we have visited all vertices which are at a distance 1 or which are adjacent to the vertex A. Now, we will pick up L1 and pick up the first vertex in L1 which is B. Now, from B we are going to visit all vertices which are at a distance 1 from B. So, we visit E. In this case, first we are visiting C. Now, we see that C has already been visited. So, we mark this edge as a cross edge. It is an edge between 2 vertices which are at the same level with respect to the source in the given tree. Correct. So, what we observe is B and C which are connected by an edge are at the same level in the graph with respect to the source vertex or with respect to A. So, we call the such edges as cross edges. Next we go to this and we realize that this is a unexplored vertex. So, mark it and mark this as explored edge. Now, there are no more and E is added to L2. There is now no incident. So, no edge incident on B which is unexplored. So, we go to C and from C there are two unexplored edges. One is this which goes to a node which is already visited. So, this becomes a cross edge. This also is a cross edge or U goes to F. So, finally, at the end you are going to visit all the vertices and you would have marked edges as discovery edges or cross edges. Cross edges are the edges between vertices which are at the same level with respect to the source. So, again like BFS, sorry like DFS, BFS is going to visit all the edges and vertices in a graph in case of a connected graphs. If the graph is not connected, it will do in a connected component of that graph. So, if V belongs to a particular connected component of a graph, then your BFS, DFS on V will visit all the nodes and edges in that connected component of the graph. Analysis is again simple as the DFS analysis. The running time is going to be of order n plus m, where n is number of vertices and m is number of edges. Again like DFS, this can tell whether a graph has a cycle or not, can check the connected components of the graph, can check for a simple cycle or a cycle and decide whether the graph is a forest, and more importantly, if given two vertices, it finds the path of minimum with which has minimum number of edges. Or in case if the graph is disconnected and these 2 points are not in the same connected component of the graph, it will return that there exists no path between the two vertices. So, one of the important application that where BFS can be used is when one wants to find the shortest path between 2 points in a graph. It is easy to illustrate, should be done as an exercise, that in depth first search a path will be always returned, but may not be a path which has minimum number of edges. Right. So, BFS is used if one has to find the shortest path between 2 points in a undirected graph, where you are looking at edges which has no weight, whereas DFS is useful in searching operation. We have seen that most of our search that we do in daily life fits into the depth first search pattern. Thank you.